So I suppose we can start. Assalamualaikum and good afternoon, everyone. So welcome back to another session, another what you call seminar for our department. So today we are fortunate to have Dr. Muhammad Khalis speaking a different thing from the one in morning. Okay. He will be let me introduce Dr. Khalis first. Dr. Khalis has his bachelor degree from UPM on diagnostic imaging and radiotherapy. And then he went to UTM for his master's and PhD, graduated in 2017. And he has been to the Ministry of Health and in a few places. Okay, one is at in Johor Bahru, if I'm not mistaken, and then he joined Institute of Cancer in Putrajaya thereafter. And then after that, he joins UPM. So we are fortunate to have him in UPM. Okay. Very experienced medical physicist. So I think I will not say anything further. So I'll let you take the screen.
Okay.
Please go ahead.
Okay, Assalamualaikum warahmatullahi wabarakatuh and good afternoon, especially to Dr. Ishamuddin for giving me opportunity to present this seminar. Ladies and gentlemen, my fellow friends. So my topics for today is on the uncertainty in projecting lifetime attributable risk from CT exposure. So everyone know the CTs mean the computed tomography. CT scan is a one-off imaging modality that produce high contrast sectional images. It is important modality as it help physicians to diagnose many diseases, lots of diseases, and it become of a gold standard for many diagnoses. So although it is benefits, it has despite its advantages, it has a lots of drawbacks. It contributes high dose exposure to the patients. That's why in this today I'm going to talk on the how we can estimate or project the lifetime attributable risk. It means that the lifetime risk, cancer risk to the patients. Okay. So now let's go back to year 2011, where there is a huge radiological incident that radionuclide dispersed to the atmosphere and have increased the background exposure. The dose exposure during that time, during that year, increased. Therefore, public start talking about this. Publics become concerned about this. Plus, the coverage by media, they all talk about the consequences and the possibility of the cancer risk induced by this incident. However, the International Atomic Energy Agency found that the disaster only had 0.02 millisievert of background dose exposure to the world's populations. And this kind of magnitude is similar to one chest X-ray examination. This is not comparable to CT exposure. Means the dose from CT is much higher. From one single CT chest or CT abdomen, patient will receive effective dose between 4 to 6 millisievert, which is 500 times than the normal chest X-ray. And we acknowledge this as more hazardous compared to what happened in Fukushima. Previously, in 2001, Brenner estimates the risk of radiation-induced fatal cancer from pediatric CT. This article gained so much interest and has been cited almost 3,000 times. And to conclude from his findings, there are 600,000 abdominal and head CT examinations per year annual for pediatric in the United States, and around 500 of them die due to the CT exposure. So CT was introduced by Godfrey Hounsfield in 1972, and since then CT has become the most important imaging modality due to its ability to produce high contrast sectional images. However, CT scan contribute high exposure to patients, and this has become of our concerns. Although it is controversial because it is a low dose, means probably no effect, but the radiation-induced risk from low dose exposure actually interests many researchers. In 2012, there is an article published in Lancet confirmed that radiation from CT might also be about twice as biological effective per unit dose as the mainly high energy gamma rays that predominant exposure source from the bombings in Hiroshima and Nagasaki. In response to Brenner in 2001 paper, one editor in AJR also mentioned that radiologists should be aware of the risk from CT scan exposure, especially when involved pediatrics. Although the community has several groups, they have several ideas. Those who are believe there is a significant between the low dose and the cancer risk, and those who are belittle the dose should be no effect, and those who are 50-50, but yet everyone in the community, especially in radiology, still applies the ALARA principles. Means that we still give the dose as lowest as possible without degrading the diagnostic quality. In year 2010, CT again become more controversial. There's a news published in New York Times. The patients claim that they are suffering from affiliation due to dose from CT. So we could see from the report there is a deterministic effect, although most of us theoretically believe that the dose from diagnostic radiology is almost no effect, and it should be only for stochastic effect. Okay. So again, this topic is a complex topic as it based on one single theory called as a linear non-threshold model. The effects may take decades to appear, and we could estimate the risk, but the calculation must be based on the group of population. For example, here in CT scan, the beam will be exposed on selected organ, and it depends on the region of examination. For example, if you want to do CT thorax examination, so the region of examination will cover within our chest. For CT brain examples, the coverage of the dose exposure is for the brain organ. But when we deal with the risk estimation, we want to estimate the risk, the cancer risk due to the radiations, we have to average it for whole body. Therefore, we need to incorporate the radiation risk report of the atomic bomb survivor. So this all begin with the radiations. Basically, there are two types of radiation. There is a non-ionizing radiation and ionizing radiation. And most of the medical application uses ionizing radiation such as X-ray to diagnose and also for the therapy. This radiation will interact at cellular levels and directly propagate to DNA, our molecule, DNA molecule. So there will be ionization process, and then there will be a chemical changes, and finally it will become the biological effect. In ionizing radiation, there are two types of action. There are direct action, and then there's an indirect action. The direct action is predominant with the high LET, high linear energy transfer, and directly propagate to the DNA molecule that can cause the damage. There are two types of breakage. The first is what we call as a single strand break, and second one is a double strand break. Meanwhile, in an indirect action, which predominant with the low linear energy transfer, the energy deposits and ionize the water that surround the DNA, and finally form the radicals known as hydroxyls. And these hydroxyls will diffuse with the DNA molecule and finally cause the damage. There are three conditions of the damage. First, the one is damage and then repair. This is what we call as a viable cells. And then there is a damage and it's beyond repair. The repair mechanism is not functioning properly and the damage is sustained, it's fixed. So the cell is considered dead, and this is known as unviable cells. And the last one is a damaged cells. repaired, but suddenly it is misrepaired. The cells is incorrectly repaired and mutates. This is where the stochastic event might happen. So for all this to happen, there is a timeline. Within picoseconds, we could see the energy depositions, and there is a excitation and ionization happen during this time. Within microsecond, there is a radical formations, the hydroxyls start to diffuse, and there's a chemical reaction. And in milliseconds, DNA starts to break. DNA breaks, and the base of the DNA become damaged. And within 1 hour, the repair mechanism start to initiate. Or during this time, if it's beyond repair, the damage is sustained. Within 1 day, the cell is start to mutate, and probably we could see there's a aberrations on the skin, and then within 1 year, it start to proliferate. And we could see the effect of cancer or hereditary effects within 100 years. So in 1977, ICRP is one organization that overlooked these radiological protections, and they introduced the first single protection quantity we call as a effective dose equivalence, and it is published in publication 26, 1977. So ICRP also has reviewed this radiological data, mostly from the atomic bomb survivors in Hiroshima and Nagasaki. And most of the recent updates is on the radiation wetting factor, tissue wetting factor, and coefficient for estimating cancer due to radiation. ICRP also accepting ICRU operational quantities for compliance with those limits, especially for CT scan examinations. They also emphasize the dose constraint. For example, the diagnostic reference levels, we call as DRLs, which established as a national indicator and become part of our optimization process. So what is the purpose of radiological protection? The main objective is to protect human and the environment from the ionizing radiations. Therefore, we need a quantitative description of radiation and exposure to human. So the committee come up with the term known as absorbed dose. Absorbed dose. Okay, this is the first basis physical quantity, because the absorbed dose is a basis of physical quantity, but we need to average the absorbed dose over certain organs and tissue, because our human tissue is different with the sensitivity to radiations. The sensitivity of the organs among the organs are totally different. Hence, in 1991, ICRP introduced the new term called as a effective dose. Basically, according to radiation protection principle, the dose is quantified as equivalent dose and also effective dose after they are multiplied with the radiation wetting factor and also the tissue wetting factor. Equivalent dose, which designed by ICRP, specify the exposure limits to ensure that the occurrence of stochastic health effect. This is why the radiation wetting factor is represent the relative biological effectiveness. So we are not using effective dose for risk estimation, but we use equivalent dose that represents certain organ that absorb the dose. So, and we use this effective dose to compare between modalities or to compare with different magnitude of exposure from both natural and man-made radiations. So in this pie chart, we could see that the CT examination was the highest percentage among the man-made radiations. So from this report, we could assume that the dose from CT concern everyone, both public and also the radiology community. So before we could proceed with the risk estimation, we need to define the dosimetry in CT, because the exposure from CT is unique. It is not simple as a conventional imaging, as the X-ray beam continuously exposed and move around the patient during the examination. In CT, we use CTDI, or called CT dose index, to estimate patient dose. And this concept was first introduced by Shaw in 1981. So we could get the CTDI information from the console, such as volume weighted CTDI and also weighted CTDI or CTDI with subscript W. And this is not a patient dose, but it is representing a standard 16 centimeter, 32 centimeter diameter phantom. So we use this type of dosimetry to estimate our patient's dose. So during relation to the phantom, the intensity of exposure is decreasing, especially in the middle of the phantom. This is due to the scattering and absorption of exposure. So we standardize the CTDI measurement by considering 2/3 of CTDI peripheral measurement and 1/3 of central measurement. So you could see from there, there's the equations there. 1/3 of central measurement and 2/3 of peripheral measurement. And then finally, we get the weighted CTDI value or CTDI with subscript W. So how do we measure this? We measure the CTDI using the 100 millimeter ion chamber. So this dosimeter is used for the measuring the dose from the CTDI phantom. And with this weighted CTDI value, we divide it with the pitch factor. The pitch factor denote as P, so that we could estimate the volumetric CTDI. The pitch factor is mean that one full rotation of the X-ray tube divide with the movement of the table. So it's a ratio, it's a dimensionless. Okay, again, it is important for us to understand that this CTDI volume and CTDI W is not a patient dose. It is represent 16 centimeter and 32 centimeter diameter phantom. So the ultimate, the final of the CTDI is dose length product. The dose length product is equal to CTDI volume multiplied with the length, scan length. So the LP is very important because from dose length product, we could get the, we could estimate the effective dose. So like other radiation measurement, the ultimate dosimetry will be effective dose. From effective dose, one can compare the risk with other type of exposure. In CT, effective dose is estimated by multiplying dose length product with the K factors. Okay, so the K factors shows in the table here. You could see it's actually represent of millisievert per milligray centimeter. Okay, or we could estimate the effective dose from CT by using the CT dosimetry software, or called dosimetry calculator software. For example, here presented here is a CT Expo and Impact CT. Okay. Okay. There are several factors in acquisition protocols that might influence CT dose, and we divide this into two. First is the primary factors, and then the secondary factors. So usually in most imaging practice, we will alter this both primary and secondary factor, so that we could lower the dose without degrades too much image quality. That's why the ALARA is still here. We want to make sure that we use the lowest dose as much possible, but at the same time, the diagnosis is still maintained. We could see the images properly. Okay, this is an example of CT Expo. Because why we need this CT Expo? Because we need to consider a dose quantity that presents the dosimetry for biological effectiveness. Okay, the computational phantom is a phantom that delivers the human organ information by using mathematical simulations. It is a Monte Carlo dependent, and the software also accurate and reliable. For example, here in CT Expo, we have two types of phantom. So you can see there is a male phantom called as Adam, and the female phantom called as a Eva. So the setup is very simple. What do we need is the CT geometry, the scanning parameter, such as tube potential and tube current, and finally we can get the dose output, both equivalent dose and also the effective dose, and also the rest, organ dose and so on. Okay, so how do we estimate the risk? There are several reports that we can refer to, such as ICRP, UNSCEAR, BEIR VII. So, for example, here is what we call as a BEIR VII. It's not beer, it's BEIR VII. So, lots of researchers using this BEIR VII report. I also use this for my research work. This book actually is the seventh in a series of the National Research Councils that they are comprehensively discussed on the stochastic effects as well as hereditary effects because of low dose exposure. Low dose, specifically for low dose, because we will discuss on the low dose. So most of the quantitative information comes from the studies of survivors of the atomic bombs, which dropped in Japan in 1945. So this book used the cohorts data of the survivors as the basis for predicting radiation-related risk in the population. So after this, we will discuss on the BEIR VII specifically and look at their uncertainties. Sekejap, sorry. Sorry.
Okay.
So, okay, the first we want to discuss is the Lnt model. So what is the Lnt model? Lnt model is a radiation risk model that observes the excess cancers above 100 millisieverts. So you see there's 100 millisieverts. So there's a black dot here, points at 100 millisievert and above. And this data is taken from the epidemiological studies, including studies on radon in homes, nuclear energy workers, and also the atomic bomb survivors. The low dose is when the dose is below 100 millisieverts or 100 milligray. And this region is our problem because based on the several observations by many reports, anything below the 100 millisieverts, there are several models we could look into. First is what we call as a hypersensitivity model. The hypersensitivity model tells us the low dose is riskier than the standard linear non-threshold model. And then there is a threshold model. Threshold model suggests that the low dose will be no risk. And the hormesis model suggests that low radiation dose provide good health, provide benefits. For example, we could see in the market, right, there's a lots of shopping, what we call selling these pendants or rings that emit the radiation. So they are based on the hormesis model. So they find that it will give benefits to the health. Actually, it's a baseless fact, but it doesn't matter because it is presented here. It's below than 100 millisieverts. And for UNSCEAR defined that the low dose is anything doses that below 100 milligray and 0.1 milligray per minute for 1 hour. The low doses and low dose rate relatively lower than high dose rate. So that's why there's a magnitude of reduction, and we call this as a DDREF, dose and dose rate effectiveness factor. So the DDREF1 is our linear non-threshold model. It's a value as a number 1. And then if it's a DDREF is more than 5, it means it's a threshold model. And in our reference here, the BEIR VII using the DDRF set at 1.5. So what is a BEIR preferred model? So the BEIR preferred model is based on cases diagnosed in period 1958 to 1998 after the bombing of Hiroshima and Nagasaki. It also based from the cancer mortality. There are two types of cancer we look at. First is the solid type cancer. Solid types mean the liver cancer, the thyroid cancer, breast cancer. That's a kind of solids. And then second one we call as a leukemia. Leukemia is a blood cancer type. So based from that, we look at the linear dose response functions, and we come up with the two types of models. Well, first, this model we call as excess relative risk (ERR), and then the excess absolute risk (EAR). And these models greatly depend on the location, gender, age, exposure, and attained age, as well as birth cohort. So based on all the epidemiological data from the atomic bomb survivor, the committee observed there are two types of categories. First, there is exposed subjects with the disease, with the cancer, I mean, and then the exposed subjects but with no the disease, don't have the disease. So the committee come out with these photo tables. Means that there are four possibilities. First, those who are exposed and get the disease. Those who are exposed but not with the disease. Those who are not exposed but has the disease, and those who are not exposed and doesn't have the disease. And from this, we classified the case into two rates, two kind of rates. The first rate is the R with subscript E. The R with subscript E, which means that the rate of disease among the exposed subjects. And then we have the second one is the R with subscript N, which means that the rate of disease among the unexposed subjects. So from this we could finally develop our first model. The first model is called is a relative risk. Relative risk means rate of exposed divided by the rate of unexposed. These measures are commonly used to compare the disease rates between exposed and unexposed subjects. Okay, so finally we get this ERR. The ERR basically is relative risk minus 1, which we could understand that the model is R with subscript E minus R with subscript N. The difference between the rate of among exposed and among unexposed, we call this as a attributable risk. Okay, so other than relative risk means ERR, and the other one is what we call as a excess risk. Excess risk, or from the BEIR VII report, it means that this is a EAR, or excess absolute risk. Excess absolute risk is expressed as a number of excess cases of or death per person year, or per 1,000 person year. Okay, both models allow one to calculate the risk of cancer at a given time of exposure. So it means that the value of the ERR and the EAR is depend on the age and gender of the subject at the time of exposure. For example, this model will tell us that the risk of cancer to a 30-year-old subject who received 1 gray at age 10 will be different from that of a 60-year-old subject who received the same dose at age 40. Okay, that's an example. It will be different, although the difference period is the same, 20 years. But the model tells us that we receive the relative risk of these two samples will be not the same. Yeah, will be the same. Although the exposure is the same, but the difference is their age. Okay. Okay, the final model after EAR and ERR is LAR, okay, or what we call as a lifetime attributable risk. From LAR, we could estimate the lifetime cancer risk. So the equation of LAR is EAR, excess absolute risk, that correspond to the dose, age of exposure, and attained age multiplied with the survival rate. So, so you could see there's a lifetime attributable risk, and actually become decline according to age, right? And also the between the gender also different between male and female is different. It's a this is how we look at based on the atomic bomb survival study. Okay, so the risk estimation is straightforward. What do we need is the risk coefficient and also the organ equivalent dose. The risk coefficient, we can get it from the ICRP 103 publication, which the value is derived from the atomic bomb survival data and incorporate with the cancer incidence of United States populations. So this nominal risk is actually is exemplified for the US population. The nominal risk is per 10,000 per sieverts. So you could see from the table, there's a nominal risk coefficients, and the left side is a organ, the type of cancer, the cancer site. There will be esophagus, stomach, colon, liver, lung. So if we take the liver, for example, the risk coefficient for developing cancer per 1 sievert is 30 out of 10,000 populations. So as previously mentioned, the risk, the ERR, the EAR is dependent to the location. It depends to the locations. So since in this data is exemplified for United States based on the atomic bomb survivor. So how about the Malaysian populations? So we cannot use this nominal risk to predict our Malaysian populations. We need to transport, to bring the atomic bomb survivor data to Malaysian cancer incidence. This is what I want to do. Okay. Okay, now let's look at the BEIR VII report. Previously it's ICRP, now it's a BEIR VII report. So this report has about 430 pages. And don't worry, we don't have to read it all before we could estimate the risk. Usually people just go straight to the table 12D1. And from this, we could calculate the LAR of specific cancer incidence. This table provides risk coefficient of specific cancer site. You could see there's a specific cancer site based on the gender, males and females. And also their age, the age here. And it is very simple. I will show you. Okay, so how to calculate the LAR of cancer incidence. So for example, there's a 10-year male receives a dose of 10 milligray to the colon from CT scan. Okay, table 12D1 shows the estimated lifetime risk of colon cancer for a male exposed to 0.1 gray at age 10 is 241 per 100,000. So you could see, if it looks at this, the patients are males, his age is 10 years old, and we see that the LAR of 10 years old at 0.1 gray is 241 per 100,000. So now patients is receiving 10 milligray, right? So we use this simple equations. LAR is a dose divided by 0.1 gray multiplied with the coefficients that respect with the age and gender. Okay, so 10 milligrams means 0.01. 0.01 divided by 0.1 multiplied with 241. So the LAR of a 10-year-old male patients who receive CT scan 10 milligray is 24.1 per 100,000. So among 100,000, 24 of them will get cancers of colon. Okay, colon cancer. Okay, so but again, this is for US populations, and we need to adjust this for Malaysian populations. So we hope we could reduce this bias. Okay. So how do we transport the risk? We know that law is dependent to ERR or EAR. So our lifetime risk estimates using the absolute risk transports, or it is depend on the EAR models. Okay. So the EAR models is obtained by multiplying EAR with the ratio of the gender and age-specific mortality and incident rates of the Malaysian population. Okay. Okay. So furthermore, the EAR also dependent on type of cancer. It will be solid or leukemia. So the EAR is formed by the equations. So you see the equation which incorporated corrective values which depend on the type of model and gender. So according to the atomic bomb survival calculations, the EAR excess absolute risk is depend to the gender coefficient value as well as dose. So D is dose, the beta with subscript S is the coefficient, gender coefficients. And we need to derive this law. It is recommended to use the equivalent dose. So D is the equivalent dose. Then we need to take into account the multiplier, which presented in equation denote as a gamma. So you see from the table 12.1, there is a multiplier. It's called as it's denoted as a gamma, and also we need to take into account the exponent value of attained age. So it represents as this model is represented as a eta. So you can get it from BEIR VII table 12.1. Okay. Okay. So this is a Malaysian Cancer Registry report. So the probability of cancer survival can be obtained from this report. This report is come out every 10 years by the Ministry of Health and focus on the 10 most common cancers among Malaysians. So the term used in the report is different than the BEIR VII report. So we have to be careful before we make the estimations. Okay. For example, the definitions of cancer registry is cumulative R from our cancer registry, right? It's actually the same as the probability of surviving until HA. Okay, and CR is the same as the conditional on survival to HE. Okay, CR. While if you want to get the ratio of mortality and incident rates that gender age dependent, you can look at the CR74. It's represent differently, but actually it's the same. So we have to bring this and put it in our calculations. So finally, we will get our law. The law is adjusted. We adapting this all the information that we have, the atomic bomb survivor, nominal risk, and also our cancer risk registration. We could finally establish our own law based on the Malaysian populations. But I need to remind you that this is for the specific cancer. In Malaysia, cancer registry report, we have only 10 sites of cancer, or we could look at 10 types of cancer. Okay. And finally, this is our adjusted law. Okay, our adjusted law, you could see there is males and females. And of course, breast cancer is #1 killer among cancers in Malaysia. So the law at age 15 is 1,645 per 100,000 per populations. But this if that organ receive 0.1 gray, it's almost like 100 milligray. 0.1 gray, 100 milligray, of course, yes. That's why usually in mammography, it's only take about 10 milligray, 5 milligray. So if we stimulate this amount, so the higher probability for getting the breast cancer, or every cancer you can try to calculate. Okay, colon, lungs. Among males is colon, colon cancer. But still, and those who are younger will receive highest law. Okay. So to summarize this, ERR and AR models is depend to gender, age, and type of cancer. This we discussed this, right? This either is it's males or females. We take all into account. So the lifetime risk can be estimated by incorporate the probability of survival until attained age. So we could reduce the bias in estimation using our established country cancer registry reports. And in the future, we need to personalize the risk estimation, if it's possible, because our current calculation is based on for populations, for 100,000 populations. But mostly patients come to the center, to the diagnostic center. They directly ask doctors or everyone's there. So, what is the probability of getting cancer due to these examinations? We cannot answer that. It's not possible. It's not for personalized. But we in the community still going on that, how we want to personalize all these estimations. I think that's all for today. I would like to thank everyone for listening. Thank you. Go back to the Tisham if any questions.
Thank you, Dr. Khalis. An interesting talk, especially for those who have not encountered this kind of knowledge before. So I welcome any questions from colleagues. Please raise your hand. Maybe I'll start first just to get the ball rolling.
Okay.
You did mention towards the end that this is not implement the law, the lifetime assessment risk, right?
Attributable.
Attributable risk is it's not meant for a personal kind of
yes
assessment, but probably just a population kind of assessment. Is it how is it being used? I mean, for example, given the kind of say statistics that we have, you are able to advise doctors to how is it? I mean, how is it being used?
Okay. Okay. Thank you, Dr. Shamari. It's very good questions. So there will be two kind of dose in the hospitals or in clinics. First is our patient's dose, patient exposure, and then second one is occupational exposure. Most of us interested with this occupational exposure. I mean, patients, because patients are not knowledge like us. Usually, the physicians are very knowledge about this. They want to know. Even if our patients are physician, of course, they are interested to know, right? Because they understand the consequences, the risk from the radiations. But most of our patients are not doctors, not physicians. they are not interested on this. But if we work in the community, I mean in the radiology department, the radiologists or oncologists or cardiologists, they are very interested with the amount of exposure they receive and what's the lifetime risk, because they understand they receive the dose, they receive significant amount of doses. So this is where radiologists, physicists come to. We have to calculate this possible risk. And also we did for the patients, if only patients ask. If patients didn't ask, then we are not calculate. But we could give some average now. If you get one chest X-ray examination, for example, you will receive about 0.02 per 100,000 populations, which is very low. So that's why you don't have to worry if you get these chest X-ray examinations. But if you doing CT examinations, for example, for those who are cancer patients, right? Cancer patients, they will every time they will get this CT screening because you want to see the malignancy. So we have to accumulate the exposure. They are not using, they are not scanned one time. They are scanned like 10, 20 times. So each time is 4 millisieverts. So you could calculate if 20 times is already 80 millisieverts. That is very high. And then we possibly have to tell them, usually will receive recurrence of cancer due to this exposure. But in medical practice, there's be no limits for patients. I mean, the doctor can request as much as possible. But we as a physicist need to aware of this. We have to tell doctor, you can use this kind of X-ray. You don't need to request some more because doctors like to request more of the images while the images is already there. But we consider this is a bit unethical. But the important is the diagnosis must be outweigh the risk. The benefits of the diagnosis must outweigh the risk. This is most important. If we continuously scan the patients, but the diagnosis is not there, we cannot see, cannot give report on the disease, the cancer, then there will be a problem. Patient will be a problem, and also the machine also, because we can use it, right? Okay.
I saw Nizam posting a question in the chat. Maybe Nizam, you want to ask orally?
Assalamualaikum, Dr. Yazid. Dr. Yazid pula. Dr. Khalis.
Ciao. Okay.
Oh,
Yeah,
can you hear me?
Please
Can you
go
hear
ahead.
me clearly?
Yes.
Okay, thank you. Okay, if we look back to the previous case in 2011,
Okay.
when the earthquake hit the Fukushima Daiichi, so the Fukushima Daiichi accident exposed certain of radiation. In other words, the radiation exposure is flying anywhere. If I'm not mistaken, from what I had read before, we found some article mentioning about the local coastline in the East Coast area in Malaysia.
Yes.
From your, I do not know, from your reading or from your research finding or research discussion with other researcher, do we have any data mentioning about the accident exposure to our East Coast area? I mean, like radiation came from the Fukushima Daiichi nuclear power plant.
Yes. Okay.
Do we have any data measuring about that?
Yeah, previously we went to nuclear agency together, right, Dr. Mosh?
Yeah.
And
But this is from my, I have no idea about that issues, but maybe you have from the data, from the...
So we also simulate these situations, and we have a radiation detector, radionuclide detector, specifically for cesium-137, cesium-134, because why is for cesium-137, 134? Because this is a man-made radionuclide. So we understand that when the nuclear reactors explode, there will be dispersed this radionuclide, this kind of radionuclide. And 1 week after the explosions, our detector in Cameron Highland, there's a one in Cameron Highland, they provide, it receive, it gives signals. There is a particles or dispersed particle in Malaysia. It's already, from the explosions, and we receive a significant, not significant, just a little bit. There will be a peak there on the signal, on the radioactivity of the cesium-137 and cesium-134. So I would say that the radionuclide is actually dispersed and already here in Malaysia, but in very small amount. So the other way is we have to collect all the soil sample in Cameron Highland along the coast of Terengganu or Pahang. So probably we will get this data to read about is the cesium-137, because it is very small, right? It's a particulate matter. I think it is not easy lah. We have to collect all the samples, all the soils along the way. So it reached the Cameron Highlands. Okay, so can I answer? Okay, I hope that will be answered, Dr.
Okay, thank you.
Okay, thank you very much. So what organ from recent report on cancer most of the Malaysians? Still colon. So, okay, if we look at the cancer report, this is latest 2007, 2012. So probably the next is this will be coming in 2021. Okay, so you could see there's 10 types of cancer. We have breast. Breast is number 1. Second is colon. This is most of the males. Breast is for females. And then we have trachea, lymphoma, nasopharynx, leukemia, cervix, liver, ovary, stomach, and others. So in ranking, the breast in colon. We have all of this. We have all the patients get this type of cancers. You could see along 5 years, for 5 years, data collections, 100,000 get all of these type of cancers. Okay, I hope that will be answers. Yes.
Khalis, any plan in the future for the COVID-19 patient?
COVID-19.
Yeah, any plan for you for your research in the future? You are plan to gather some information related to the COVID-19 patients?
Because my expertise is in the radiation dose, I would like to gather some information, the dose exposure from the chest X-ray examinations and CT examinations to COVID-19 patients. I have to get the data from the MAEPS especially, and also in several hospitals.
So you are planning to get all those data in the future?
In the future. But let's this COVID-19 rest a bit, then because my studies are more on retrospective only. It's very simple compared to all of you.
And the Sedang hospital is not safe anymore, isn't it?
It's become already COVID-19 hospital. All patients are clear out. All the what become COVID-19 patients. It's uncontrollable now.
Okay, there is another question in the chat. Lokman, you want to raise the question or I read it for you?
Very great. Okay, so just now Dr. mentioned that when we use the CT scan, maybe there are high dose that will received by the patient, so it might be dangerous for the patient. So why not we just use MRI or maybe X-ray to scan the
Okay.
image? What is the condition that make us need to use the CT scan for the patient? Thank you.
First, the CT scan is very fast. It's very quick. You can get the data in within seconds. And also the resolution is much better than the chest X-ray, and then the general X-ray. And with the same time, you can get a lot of information. That's why most of trauma patients, those who are accidents, when come to emergency, the first they will do is the CT brain or other part lah. If you could look at their conditions, extremities and so on. We cannot use MRI. MRI is one region examinations will took about 30 minutes to 1 hour, and it's very long process. For example, I give you example in my previous hospital I work in Mahkota Medical Center. We receive one day we could diagnose 500 patients of CT examinations. Almost 200 200. But for MRI, we could allow only 10 patients because the examination is very long. We took so much many because this is using this MR concept, right? The resonance, and for this data to be collected, they took lots of time. One patient probably we need 1 hour to 2 hours for MRI, and MRI is only for very special examinations. For example, like we need to see the soft tissue. MRI is very good for the soft tissue. It's not like CT scan. CT scan is more like bone and some soft tissue. But to become more detailed, the spatial resolution is much higher in the MRI. But it's only for certain conditions, not for all. Everyone will come first. The first frontliner is CT scan. MRI macam lauk lah, CT scan macam nasi. Tak ada CT scan, tak boleh makan juga kan. Okay.
Thank you.
Okay.
Any more questions from the?
Dr. Shah, maybe I have one question for Dr. Khalis.
Okay.
Okay, my friend, Dr. Khalis, maybe you can share with us what is maybe a new field that related to the CT scan, because we know that the CT scan is well known for the medical, right? So maybe for your future research, any new field or new point that you would like to elaborate or to focus on this CT scan field.
Thank you, Dr. Hafiz. So nowadays, most of us talk about this. There will be two. First is a dual energy CT. It means it's not like a conventional CT. Conventional CT using one single tube X-ray, but in the modern arena, in this advanced CT scan, they use two kind of tube that rotate together. That's one. And then the second one is, I don't know, I read about it recently. Lots of scientists or researchers in the developed country, they start to talk about the CT spectroscopy. I don't know what is the function. They always mention about the CT spectroscopy. I don't know what is the purpose of the CT spectroscopy yet, but we look into it after a while, because no one's discussed this in Malaysia. Okay, Dr. Hafiz.
Thank you, Dr. Khalis.
Okay.
All the best.
Okay, thank you very much. Thank you, patients.
Any more questions from the audience? It's already 4:05. Maybe I have one last question, a very basic question, I suppose. you had the BEIR model, right? That was supposed to come from some data set of the survivors of the atomic bomb survivors,
Yes.
and then you get all this law data from the one that you showed just now was for US, and then you wanted to transport this to the case of the Malaysian.
Yes, yes.
What is actually involved between, say, between the data set of the atomic bomb survivors going to the law data of, say, the US, and then transport it to the case of the Malaysian? What's actually involved inside this? No, the transportation of this assessment risk.
Okay. First, of course, our cancer registry report. There's a variable that totally influence our law. And then the second one is our types of cancer, and most of that is dependent. It's become dependent variables. And for example, the dose we maintain same 0.1 gray. It's mean 100 milligray. And the only changes that we made is we need this ratio, the ratio of survival, attain age, and the exposed age, because our Malaysia cancer registry report, the population is until 74 years old, but in US population, the incidence report is until 80 years old. So there will be some difference because when we try to get the ratio, of course there will be it is very significant to the calculations.
So most of it is because of the difference in the statistical data set.
Yeah, because and also this will be changed after this. The cancer registry report will come out. Probably the breast become lower. We don't know that. Then we have to build up another law for Malaysian population. We try to adapt all of this.
Okay.
All the way with the changes.
Perhaps I think, if you don't mind, another question from me.
Okay.
We saw that the case of the differences between the female and male, the risk assessment is higher for females, and that was shown for the case of the US citizen. I'm pretty sure it's also the same for Malaysian.
Yeah.
Right.
Yeah.
So, is there any particular reason for this, or no?
Yes. Yes.
Biological makeup.
Yeah. Good questions. Because if you previously remember in my slides, each organ have their own sensitivity, and of course, we consider females have a lots of sensitivity due to radiations, especially the breast. Breast has a higher sensitivity to these radiations, and also their ovary and so on, compared to what female have. Female for mostly female probably also the cancer risk is not due to the radiations. It's really due to the food thing, smoking preference. And because the sensitivity organs between females and males are different. Okay,
Right.
I hope. Okay, sorry.
I guess if there are no immediate questions from the rest, let me put a countdown: 5, 4, 3, 2, 1. Okay. So I think let's us thank Dr. Khalis again for this interesting talk, and thank you very much.
Thank you, Dr. Sham, for giving me this opportunity.
Okay, I will stop the recording now, and no, we can proceed to chat if you want.
Yeah.